x. And on the left here, you got e. So you undo e. This is key. You undo e with natural logs. You take the natural log of both sides of this equation. Okay. And then you actually move this x out front. It's x natural log of e equals natural log of 5. The natural log of e is 1. So this becomes x equals natural log of 5. A lot of students will just go right to this line right here, but this is the full explanation of it if needed.
Okay.
Now over here, you already have an ln. So you undo ln with e. You use e on both sides of the equation. It's e to something, e to something, e to something to do that. So on the left here, like there's a little bit of hand waving, but it just becomes x on the left. These undo each other. On the right, it's e squared.
Alrighty.
Is that clear?
Yep.
Great. Let's take a look at 14 here.
14a.
14a.
So you would take the natural log.
Yes.
Of the left and the right, obviously.
Yes.
That would cancel out the first e.
Yeah, it's a little weird here, but yeah, it's like you just said. What it becomes is e to the x equals the natural log of 2, but you're not done because you got to do it again.
Right.
Natural log e to the x equals natural log of 2. The left, as we just talked about, that x comes out in front, but this shortcuts to x equals natural log of the natural log of 2.
Right. Okay.
Good. Are we doing B?
Yes, please.
B, I recall when we did this before, this was just, it was weird because it's like, I got to tell you the answer to do it. It's not E or ln. So it's like, this is really asking the tangent of what angle equals 1. And so there's 2 options here. 45 degrees or pi over 4 in the first quadrant is true, but arctangent is only valid from minus pi over 2 to pi over 2. So our answer has to be in the first quadrant here. So again, there's like no ln. I don't quite get it, but that's what it is.
Just a random.
Yeah, I don't get it, but what it is. So all right, back on the path here of questions associated with E and ln. All right, so on the left here, to solve an equation like this, whenever you have ln and ln, 2 of them like this, you want to compress them or condense them. So your goal is to get the natural log of something equals 1. So we're gonna combine these using this property, the natural log of a plus the natural log of b. That becomes the natural log of a times b because it's a plus. So this becomes the natural log of x plus 1 times x minus 1. Okay, now you can choose to FOIL it now or later. You will have to FOIL it eventually. I'm going to FOIL it here. It becomes x squared minus 1. Okay, now just like in the previous problems, we undo ln with e. So e undoes the ln. E is needed over here on the right. So you have x squared minus 1 equals e. Again, you're solving for x. So you add 1 to both sides. X squared equals e plus 1. And then you take a square root. X equals plus or minus the square root of e plus 1. But you have to check for extraneous. Okay, so if you go back to your original here, the natural log, the domain of natural log is from 0 to infinity, meaning you can't take the natural log of a negative number. So when you put in the negative, if you have a negative out in front, for sure in this one over here on the right, it's going to be negative. I'm not so sure about the one on the left, but for sure over here, you're going to have an issue because it's going to be a negative number minus a negative number or minus a number, still negative. So it's undefined there. So your only answer is positive square root e plus 1.
Alrighty.
All right, I'm going to grab b and just work it down here vertically, just because that one took up a lot of space. So this is the first log base b, and you undo the base 5 in this problem by writing 5 to the log base 5 c to the x. And then over here, it's 5 to the d. So these have to match, just like we did with e in the last problem or other problems. So the 5 undoes the log base 5. So that is always the case. You just get c to the x equals 5 to the d. Okay, and now you got to undo c. You got to get x out of the exponent. The only way to do that is with ln. Natural log c to the x equals natural log 5 to the d. This becomes x times natural log of c. And then you got to divide both sides by the natural log of c. And none of this is calculus, by the way. This all leads to the calculus. It's like a review. It's like, if you hadn't seen it, here's a few review problems, and then we're going to go off and do our calculus. Do you want any problems like this? Should we move on to something else?
Let's move on. It's the very bottom picture, the 17 through 43 ones.
Okay.
Obviously,
Lots of fun. Yeah, lots of fun stuff here. You gotta lead me here, because this is all review. So like look for ones that either seem unclear.
17.
All right. Okay, so we're taking derivatives. So what is the outermost function of this? And it's the ln, right? So ln is 1 over whatever's inside. Okay, then chain rule says, okay, now we got to take the derivative of what's inside. And again, you're just looking at what's inside, and that's now a product rule.
Right.
So it's x times the derivative of natural log of x, 1 over x, plus natural log of x times the derivative of x, which is 1. And then you are actually done there. Okay. Whether you simplify or not depends on the instructor, or the questions on the exam, whatever it says there.
Yeah, you can just leave it.
All right.
We can leave it like that.
Perfect. What should we do next?
Or wouldn't x times 1 over x be
1? This one actually kind of
Okay.
works out nice. I mean, it's
Right.
1 plus natural log of x, and then like if you put this over x natural log of x and this over x natural log of x, you get these cancel, and you get 1 over x here. So you actually factor out an x. It becomes 1 over x, 1 plus 1 over natural log of x. I mean,
Right.
I don't know. It's but the only helps if you're going to do something with it.
Let's do 19.
Sure. So what do you see in 19? Like, what's the overarching derivative rule to use on this one?
Rule.
Quotient rule. Good. So you got to know quotient rule. You will use this in Calc 2. It's expected that you do it fast. So that's, just it's not going to get away with it. So it's your derivative here is the bottom times the derivative of the top. The derivative of e is itself, but then there's this chain rule. So 1 over x is negative x to the negative 1. So its derivative is negative x to the negative 2, which is better written as negative 1 over x squared.
Right.
Although you could leave it like that, but it's your choice. Minus the top times the derivative of the bottom. The derivative of x squared is 2x all over the bottom squared.
It looks a lot more complicated just looking at the problem.
Yeah, it sure does. I mean, that's it. You're done.
Yeah.
Especially when you don't have to simplify.
Well, I guess could you like look at a problem and think of like a good one that would be easy that I could like easily slip up on or miss a step on.
Yeah, like 25 is a good one.
Okay. I'm also thinking about like he said, him saying he was gonna pick like the easier problems of the each type.
Yeah.
So I'm trying not to do kind of like pointless ones basically.
Yeah, good. I was working with some earlier today and we did something really, I said, this is probably not a good problem to work on. So, all right. So derivative here, this like you want to look at three, you should see, when you see 3 to something, what you should see is e to something, because the derivative of e is itself. The derivative of 3 to something is itself with a tiny, tiny little extra, which is the natural log of the base.
Right, yeah.
Okay. And that's something you might misremember, stress of all this, but we are not done because the inside function here is a product rule.
Right.
Now we just did it, but it's x times 1 over x plus natural log of x times 1.
Yeah, I gotta study the log rules.
Yes. So like some of these, I guess I would just make comments on, like, if you'll permit me to do that. So like
Yeah, go ahead.
18, we'll look at it. We don't need to do all these, but I do want to make some comments, and you have access to the recordings and the notes as well. But this one has constants in it. So this one's really
Right, yeah.
emphasizing, like, do you know how to handle these constants? And if you need to, you can make them like 3 and 4, but like you have to know how to handle constants that are not numbers.
Right.
Okay. 20 is emphasizing, do you know all of your trig derivatives?
Yeah.
Because it could be cosecant x. We have no idea. Okay. 21 emphasizes, let me get snipped in here. 21 is emphasizing trig inverse derivatives, which
Mhm.
again, it could be
I
arctangent,
got
arcsecant,
those to memory.
great. Okay. But furthermore, it also involves what I call a rewrite step, which is, this is really tan inverse of x, just another way to write it, but it's 2 the 1/2 power. And
Right.
so like some of these require you to be like, oh yeah, that's how you rewrite them. Okay.
Is the derivative of secant tangent?
Yes.
Okay.
But cosecant is cosecant cotangent with a negative. So it's, it's like, I gotta remember all this stuff.
Hmm.
27.
We usually don't work with we haven't worked with cotangent. It's usually just secant, and cosine, all those, yeah. The normal ones.
So this little h, hyperbolic, these are a whole list of 6 derivatives that you might need to know. And like, I can't tell you whether they will or they won't. If you have a session with your instructor, I would ask, like, do I need to know the hyperbolic ones? They'll probably say yes, but you can at least ask and maybe
Yeah,
get.
I haven't ever seen anything like that.
Right. So you got to be careful you don't, start going down into the weeds. Now
Yeah.
we should do like a 28. Okay.
Okay.
Because you for sure need to know how to do an implicit derivative. Okay. So this is an implicit derivative. Okay. So on the left here, this is product rule. So is it on the right. So product rule. So it's first times the derivative of e to the y. So the derivative of e to the y is itself. But whenever you have a y, you have to include a y prime.
Okay.
Okay, very important here. And because it's product rule, you gotta remember this creates 2 terms, this creates 2 terms. So you're not done until you get the next terms. So it's e to the y times the derivative of x, which is 1. Okay, feeling pretty good here. Now we got to go to the right-hand side and do the same thing. So it's first times the derivative of sine is cosine. Okay. Oh, as an aside here, you definitely want to know your unit circle.
Yeah.
That could be a thing to, spend 15 minutes on at some point, really making sure you know.
Yeah.
All right, plus sine x, derivative of y is 1, but because there's a y prime. Okay, so now you want to get y prime on one side. So I'm just artificially choosing to move left and everything else right. So this is x e to the y prime minus sine x y prime equals y cosine x minus e to the y. Then you factor out y prime. So you get y prime x e to the y minus sine x e to the y. Then you divide. So you get your y prime equals y cosine x minus e to the y over x e to the y minus sine x.
Alrighty. We can move on to a different section. Let me go look.
I mean, there's a lot here. Like if it were me, I would try and do these on my own, as many as I could,
Right.
you know, time
Yeah.
permitting. And there's tons of online tools also that'll even step you through some of these as well. All right, so where to next?
Let me.
We can take a minute or two also just to take some deep breaths. Really. All right.
The evaluate the limit 61 through 76, those
Sure.
ones.
Sure.
And we're just doing like 3 of them.
61 through 66, you said?
Yeah, that section, or wait, 66 through
66 through.
hang on, it's just through 69. If a couple of those are like too complicated or too like specific.
Yeah, so this one here, like you got to know what to do, which is hard when you're learning this. You know, like you probably heard me say, your instructor say, like just put the value in, but with infinity, it's a little weird. But you can think of it, okay, e to the minus infinity times sine of infinity. Well, that's kind of weird. Okay. Now it ends up being 0, but not for this reason right here. So let's rewrite this slightly. This is the limit as x goes to infinity. Okay, e to the minus x times the limit as x goes to infinity of sine x. So what do you know about sine? Sine oscillates, right? Boom, 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 boom. It is always bounded from -1 to 1. So that doesn't seem to help much.
Mhm.
What does the graph of e to the minus x look like? Well, it goes boom down to 0. So this is 0. So thank goodness, because 0 times anything is
0.
0. And that's, I mean, that's kind of what this is. You shouldn't really do this where you put infinities in, but you know, it's sort of okay. But this, the big thing here is you get 0 times something gives you 0.
Uh-huh.
All right, 67.
Yep.
Okay, so there's kind of a rule for this one as well. Like when you go to infinity, you have to kind of like think about, well, what happens when you add one number at infinity? Well, it doesn't contribute anything.
Uh-huh.
You know, $1 billion plus one more dollar is still $1 billion. Okay. Now I know there's a negative down here, but it just means you're at negative $1 billion. So if you add a dollar, it's still really big. So essentially, like this looks like 2 to the x over -2 to the x. And there's a ratio here. Okay, like these are the same. So it's equivalent to like x to the 5th over negative x to the 5th. Whenever these match, it's just the ratio of the terms out in
Right.
front. So it's the same thing here.
So it'd be -1.
Yes.
Okay.
68 is one of those kind of exceptions, weird ones that we can do, but it's in the category of I wouldn't do it.
Okay, that's fine.
But 69, 70 would be good to look at. Um,
69.
did you say L'Hopital's rule would be included or not?
Oh, that'll definitely be on the test. Yeah.
Great. So it's kind of weird because you get back to these questions and you were doing limits in the beginning and then they bring it up again in the class. So you always try the numbers. So it's like e to the 0 minus 1 over the tangent of 0, and you get 0 over 0. This is called indeterminate form. Indeterminate form. Okay. And there's other ones. There's like infinity over infinity. And I think there's one or two others. When you get this form, you have to take the derivative of the top and the bottom. It is not quotient rule. It's the top over the bottom. So what's the derivative of the top? Derivative of e to the x is itself. Tangent is
Secant.
Secant squared x. Okay. Then you try the numbers again. So you get e to the 0 over secant squared of 0. This one actually works. You get 1 over 1.
What's the derivative of secant squared? Is it just secant squared tangent squared?
It's 2 times secant of x because that's power rule. But then the derivative of secant is secant tangent. So it ends up being itself times tangent of x.
Oh, okay, that makes sense. Okay.
And if you take another derivative, it ends up like you see a pattern, and you see you'll have some problems in calc too like that. Okay, now I want to go back to this problem right here because we actually could have used L'Hopital's rule. If you put infinity in, 2 to the infinity is infinity over 2 to the infinity is infinity, but it's negative. This is also indeterminate form.
Right.
Okay. And that's why you don't have to do any of this like hand waving or like, what is it? You can actually just be like, oh yeah, I know how to do this. It's L'Hopital's rule. The derivative of the top is, think of 2 to the x as e to the x. It's 2 to the x with the added little wrinkle of natural log of 2 over, okay, 2 to the x, natural log of 2, but there's a negative here. And then you can cancel stuff. So this becomes the limit as x approaches infinity of -1 because everything cancels, which just equals -1.
All right.
Way easier than like me trying to explain like what happens at infinity.
Yeah.
But you don't know derivatives yet.
All right, let me look and see which ones. Oh, the absolute extreme local and absolute extreme values of the functions.
Yep. 1, 2, 3. These are 4. These are all pretty long. I think we've even done like number 1. Do you have a preference here?
Just do number 1 to refresh my memory. I don't remember.
All right. So the whenever you're given
number 1, I don't know how to do the other ones.
So whenever you have a closed interval like this, you want to first, I like to first test the endpoints to get the values.
Right.
Okay, so that's 2 cubed minus 6 times 2 squared plus 9 times 2 plus 1. And then 4 cubed minus 6 times 4 squared plus 9 times 4 plus 1. So you do not get a calculator. So we got 8 minus 24 plus 18 plus 1. So that gives you 26, 2, that gives you 3, it looks like. And then we got 64 minus 64 plus 36 plus 1, you get 37. I'm pretty tired, so definitely check these later. All right, so there's no calculus. That's just, the can you evaluate the endpoints? Yeah, I can evaluate the endpoints. So now you take the derivative, okay?
Right.
Now on like 2, you got product rule, you got power rule, quotient rule in there. 3, you got quotient rule. 4, you got product rule with a little quotient. I'm sorry, with a little chain rule. I misspoke. 2 is a product rule with a chain rule that is power rule with some chain rule. So anyway, the derivative here is 3x squared minus 12x plus 9. You want to set that equal to 0. So you have 3 times x squared minus 4x plus 3. Factor that, you get x minus 3, x minus 1. You get 2 critical points. You get 1 and 3, but they have to be inside this window.
So 3 is the only right
So,
answer.
so 3 is there. So now you got to go back. And I like to go, actually, I should have left a little more space because there might have been 2. I like to go in and because you're really just comparing these 3 numbers here. Okay, so we got to go back and get that. So it's 3 cubed minus 6 times 3 squared plus 9 times 3 plus 1. So that's 27 minus 54 plus 27 plus 1. That ends up equaling 1.
So what's the purpose of doing the first 2 things you did, plugging into the equations?
Because to do the absolute extremas, which we're going to do first.
Oh, right. Yeah.
So
Right.
let me, because I would like to just, I'm going to just copy this down so we can do our actual like analysis. I got this too jammed up here. No, that was bad. Okay. All right. So which is the biggest? 337 or 1?
I think it's 37.
Okay. So that's your absolute max.
Right.
And 1 is your absolute min. Okay. But we have more that we can do here. So because they could be relative min. So we're going to make a really very basic sketch here of what's going on. So it's 2, 3, 2, 3, 3, 1, and then 437. Okay. So the graph looks something like this. Now I drew a horizontal tangent there because at 3, that's one of the derivatives. Okay.
Yep.
You see that? So 3, 3,1, it's also a relative min because it's the critical points correspond to relative mins as well. Now you could also say that 2, 3, this one over here is a relative max because it's bigger than the places around it.
Right. So yeah, okay. So that's how you find the maxes, and then what does the problem say again?
That's it. That's everything it's asking for here.
Oh, okay. Oh, right. Okay. Sorry. I'm just. Can we do number 4 and then honestly we can be done after number 4.
Okay, let's take a look at it. The recipe here is exactly the same. So you want to evaluate it at the 2 endpoints. Okay, so that's -1 squared e to the -1, and this is 1 times e, so it's just e. Okay, and e for reference is 2.7-ish because you may not be sure like well, what is it? And then 1 over e, it's about a third, so it's about 0.35-ish. Okay, so f of 3 is 3 squared, e to the -3. So that's 9 over e cubed. Okay. And I know you don't have a calculator, but like it's okay to just say what they approximately are. E cubed is like 3 cubes. So this is like this is like, it's like 9 over 27. So it's about 0.3-ish. Right in there. It's definitely smaller than that. Okay. Now you get to be able to take a derivative. What is the derivative rule that you see here? Product rule. So it's x squared, derivative of e is itself, but then you have to multiply by -1 because that's the chain rule part of it.
Right.
Plus, okay, e to the minus x times the derivative of the first, which is 2x. All right, is that okay? Is that clear?
Yep. Just equal all that to 0.
Yes, set it equal to 0. So we're gonna do some factoring for this.
Okay.
On this one, let me just fire off this message real quick. So we got, let's factor out the e to the minus x. Okay. Now, normally you put the x squared first, but see how it's negative. So I'm gonna actually put the 2x first, minus x squared. So now you're going to set 2x minus x squared equal to 0. E is never equal to 0, by the way. So you can factor out an x. So you have 2 minus x equals 0. So x equals 0 or x equals 2. But we have to check them on that interval again, that -1 to, what did we say here? 3. Ooh, they both hit. Okay. So we got to check them both now. See how they're both in that window?
Right.
So we go back. I didn't leave enough space. Darn it.
Is usually one supposed to cancel out, or?
Yeah, usually one's not in there, but they could be in. I mean, just the nature of these things.
Yeah.
So f of 0 is 0 because it's 0 squared times whatever. And then f of 2 is 2 squared e to the minus 2. So it's 4 over e squared. It's 4. It is about like 1/2-ish.
Yeah.
Okay, so now you look at these 4 numbers, 2.7, 0.3, 0, and 0.5. Which is the biggest? Which is the smallest? Absolute max,
Mhm.
absolute min.
Alrighty. Yeah, we could wrap up there. I'm sure you're how many lessons you have today?
Don't worry about that. If you need more time here, I'm totally
no,
good.
I'm good. I was
I don't know, 6 or 7 already.
Oh.
Yeah, everybody wants help at the same time.
Yeah, it's probably exam week for all.
It absolutely is. But I really do appreciate you scheduling.
Yeah.
And I guess we've got one tomorrow. So I think so. Just keep it coming. If you're spending time on your own, that's great. And we'll you'll do great. So
Alrighty.
all right. I'll see you next time. Have a great night.
All right, you too.
Bye now.